This is part 2 of lesson 6-6, systems of inequalities. We're still graphing systems of inequalities, and now we're using them to solve word problems. All right, so applying systems of inequalities in real-world problems, sometimes only whole numbers make sense for the solution, and often only positive values of x and y make sense. So that's talking about just this very first example. All right, business, AAA gym company produces necklaces and bracelets in a 40-hour week. So I'm going to highlight some of these things. Anywhere I see numbers, I'm going to highlight it. In a 40-hour week, the company has 400 gems to use. A necklace requires 40 gems, and a bracelet requires 10 gems. It takes 2 hours to produce a necklace, and a bracelet takes 1 hour. How many of each type can be produced in a week, right? Of each type of what? A necklace and a bracelet. So the things I've highlighted, that's what's important, right? We've got two things, necklaces and bracelets. We've got time. We've got a 40-hour work week. So, and actually, I'm going to highlight the 40-hour work week and the hours, 2 hours and 1 hour, and then in yellow is the gems. Okay, so in a 40-hour work week, it takes 2 hours to make a necklace, and it takes 1 hour to make a bracelet. So you can put all that together. And you have 400 gems to use, and a necklace requires 40 gems, and a bracelet requires 10 gems. So it says, let N represent the number of necklaces that will be produced, and B is going to be the number of bracelets that will be produced. Neither N or B can be negative, right? You can't make negative 2 bracelets. So it's got to be 0 and up. So the following system of inequalities represents the condition of the problem. All right, so we've got quite a few here, right? And we're going to think through these. So for the first one, necklaces have to be greater than or equal to 0. That makes sense, right? You can't make negative necklaces. Makes sense. Bracelets, same thing, has to be greater than or equal to 0. It can be 1, 2, 3, 4, but it can't be negative. 1 bracelet plus 2 necklaces has to be less than or equal to 40. What is this talking about? The work week, right? It takes 1 hour to make a bracelet, and it takes 2 hours to make a necklace, and together that has to equal less than or equal to 40 hours. Right? So however many bracelets and necklaces you make has to equal less than 40 hours. And then lastly, 10b plus 40n is less than or equal to 400. What is that talking about? We talked about gems, right? It takes 10 gems to make a bracelet and 40 to make a necklace. Well, you only have 400 gems to use total. So whatever you use for bracelets and necklaces has to be less than or equal to 400. So in all four of these equations, B always represents the number of bracelets you're making, and N always represents the number of necklaces you're making. Each equation represents something different, right? So if we take all 4 of these and we graph them on the same graph, our graph is going to look something like this. And let me zoom in on this and we can talk through it, right? Okay, so first off, here's our graph, so we can hold that steady. First off, we know that we're only working in this quadrant of our coordinate plane because we can't be in the negative region anywhere, right? Here on the x-axis, they put the number of necklaces. Here on the y-axis, they put the number of bracelets. You can't have negative necklaces and you can't have negative bracelets. So we're working just in this quadrant, everything positive. Okay, then we said that we were talking about the hours, right? You're constrained to 40 hours. So we said 1 hour per bracelet plus 2 hours per necklace has to be less than or equal to 40. So when we graph that, we get this line right here, and it's either this line or anything less than this line, right? So any of the ordered pairs in this triangle, here I'll highlight it yellow, anything in this highlighted yellow region, any of the ordered pairs there would work as solutions, right? And then we have this other little skinny triangle, and that line right there is 10b plus 40n equals 400. That represents how many gems we can use. 10 per bracelet plus 40 per necklace, and you only have 400 to use, so that has to either be less than 400 or equal to 400. So there's our line, and anything below that is all the possible combinations, you know, depends on how many bracelets you use and how many necklaces you make to know how many gems you used. So all of this, plus the fact that we're only working in this quadrant, where all of it overlaps is in this pink region, right? So any of the ordered pairs in this pink region work. Now, can we use decimals or can we use fractions? Could you make 2.3 necklaces and whatever up here, 38.2 necklaces or whatever it ends up being? No, has to be whole numbers. So that's what the directions that we're talking about. It doesn't make sense to have just any numbers in there. It has to be whole numbers. So the solution set, so solution is a set of ordered pairs in the intersection of the graphs. That's this pink region here that we highlighted. That's where all of them have stuff in common, in the little pink region. The region is shaded at the right. Only whole number solutions such as 5, 20 make sense in the problem. So you can name any ordered pair in this little pink region that consists of whole numbers. So we can't say 10.2, 3.8, or whatever. We can pick a number in here, like they picked 5, 20. So 5 would be halfway, 20 would be right here. That makes sense. It's in the pink region. It's whole numbers. That makes sense. So any ordered pair in this shaded region where everything overlaps that consists of whole numbers only, no decimals, those are your solutions to this word problem. So we could make 5 necklaces and 20 bracelets, and that would fit all the constraints that we have up here. Okay, so let's do 2 here on our own. They're slightly easier. All right, for each exercise, graph the solution and then list 3 possible solutions to the problem. Make sure you read the directions. All right, first, Mr. Flowers is a restricted diet. Mr. Flowers is on a restricted diet that allows him to have from 16 to 200 calories per day. His daily fat intake is restricted to between 45 and 55 grams inclusive. What daily calorie and fat intakes are acceptable, right? So we got to figure out our range here. Well, first off, let me find my straight edge. For calories, I know it's between 1,600 and 2,000. So I'm going to draw lines here. Calories is along the bottom. This measures calories. So I'm going to draw a line. It looks like this is 1,500. So I'm going to go slightly over to 2,000. I'm going to shade that region because that represents all the possible choices between 1,600 and 2,000 calories. Okay, so everything in here. That's how many calories he can have a day, anything between in there. Then we measure the fat, oh, sorry, I didn't realize you can see that. Then we measure the fat intake over here on the side, and it says he can have between 45 and 55 grams of fat per day. So this is 30-40, 40-50, so about halfway is 45, and about halfway here is 55. So I'm gonna draw lines, like kind of the boundaries, showing my fat intake, or his fat, Mr. Flowers' fat intake. Diets stink, right? Blech. Okay, so he can have anywhere between these 2 lines. All right, so if he has to have between 1,600 and 2,000 calories a day, and he has to have between 45 and 55 grams of fat per day, he's pretty much restricted to this one square, right? Any ordered pairs in this square right here, this is where those all overlap, all the restrictions overlap. Anything in here could be a solution, right? So we could say it's between 1,600 and 2,000. We could say 1,800, and it's anywhere in here, and 50, right? He could have 1,800 calories in a day, and that could include 50 grams of fat. 1,850. What's another ordered pair he could use? We could do 2,045, right? Right here on the bottom corner. He could have 2,000 calories because it says between 1,600 and 2,000. So he could have 2,000 calories. And he has to have between 45 and 55 grams of fat. We could even say, since it's between, we could say 1,999 calories, right? And then instead of saying the very bottom here is 45, we could say 46. Right? That ordered pair, if we were to graph it, 1999 and 46 would be almost here and just over here. So it would be in this little region, right? Or we could say he could have 1,601 calories and he could have 54 grams of fat, right? We had to come up with 3 possible solutions. So all 3 of these ordered pairs lie in this little section right here where the pink and the yellow overlap. The yellow is how many calories he should have per day. The pink is how many grams of fat he should have per day. So if he's meeting both of those where they overlap, these are all of his options, and these are 3 of them. 1,800 calories, 50 grams of fat, 1,601 calories, 54 of those fat, or 1,999 calories, 46 of those fat. Any of that works, okay? Next problem. Let me back up so we can see more of this, sorry. Can't always tell until I'm halfway done with drawing or writing that y'all can't see what I'm doing. All right, hopefully you can read that. Here it says, recreation. Maria had $150 in gift certificates to use at a record store. She bought no more than 20 recordings. Each tape cost $5.95 and each CD cost $8.95. How many of each type of recording might she have bought? So we can write 2 equations here. We can write total cost and we can write quantity, right? So total cost, we can use $150 or less. And what makes up that $150? Well, I'm spending almost $9 per CD and almost $6 per tape, right? So I'm going to say $5.95 times how many tapes I get plus $8.95 times however many CDs I get. And that has to be less than or equal to $150, right? So there's one equation. And then if T represents how many tapes I buy and C is how many CDs I buy, T plus C has to be, it says she bought no more than 20. So the most she could have bought is 20. So she could have bought less than 20 or she could have bought equal to 20. So tapes plus CDs had to total, the quantity, the number of them, had to be less than or equal to 20. All right, so we're going to graph both of these and see where they overlap, right? All right, so to graph these, they're kind of like in standard form. I'm going to figure out the intercepts. So to find the tape intercept, T, I'm going to cover up C. 5.95 T is less than or equal to 150, so 150 divided by 5.95 equals a little over 25.21. So across here, I'm going over a little over 25, about right here. And then for C, I cover up T, plug a 0 in for T, solve for C. 8.95 C is less than 150. 150 divided by 8.95, 16.75. So on my C axis, I'm going to go up to a little bit over 15 and put a dot. Okay, and then that whole equation is a solid line because it has the line under it. So I'm going to use my straight edge, wherever I put it here, to draw a line, solid line. And it's an inequality, so I can spend, here's my line, I can spend less than or equal to that amount, right? So I can spend anything in this area less than or equal to that line. I don't have to spend the full 150, but I can spend up to 150. I can't spend more than that, okay? Then the other equation, T plus C, is less than 20. So if I cover up C, I could just buy 20 tapes and no CDs. Or if I cover up T, I could buy just 20 CDs and no tapes, right? So for the the T-intercept tapes here, put a dot on 20. For the C-intercept CDs, that's 20 as well. And it's a straight solid line. So I connect. And it can be less than that too, right? It can be less than or equal to 20. It doesn't have to equal 20. So I fill all this stuff in. So the shaded region that satisfies both of those equations is anything in this area. So I have to pick 3 solutions, right? And they have to be whole numbers because you can't buy 2.4 CDs, right? It has to be 2 or 3 or whatever. So I'm gonna pick over 5 up 5. So I could buy 5 tapes and 5 CDs. I could buy 10 tapes and 10 CDs. That's technically below within that overlapped region. I could buy 5 tapes and I can't quite go up to 15, 12 CDs. 5 tapes and 12 CDs. Oh, you can't see what I'm writing. Right, so all 3 of these ordered pairs right here fall in this double shaded region. 5 and 12, I would guess, is right around here somewhere. So all the solutions in this double shaded area here, highlight it in yellow, any of those work as long as they are whole numbers. Can't have fractions. So we listed 3 possible whole numbers. These are 3 ordered pairs that fall in this overlapped shaded region. Okay, hopefully that's making sense. No big secret here on having to write out your answer in numeric form. You literally just have to graph it and leave it alone. Okay, let me know if you have questions.